The focus of our project was land development to be used for both biofuels and prairie restoration.
As an overview, I should start by saying there was a pledge around the world, in the United States and in Minnesota, to reduce greenhouse gases. Minnesota in particular wants to move to 20% renewables by 2020. This means there is a need to look into bioenergy. We currently have bioenergy like ethanol, but it is heavily subsidized despite its many problems, which means looking into low-input, high-diversity biofuels would be beneficial as they have many benefits in comparison to traditional biofuels like ethanol. We use GIS to model the effects of converting 10% of Minnesota's corn crop to LHD land.
The most obvious problem with current fossil fuels is CO2 emissions. We need to move towards biofuels. Loss of prairie lands and prairie species habitat is a huge problem that needs to be reversed. Ethanol is not carbon neutral. There are many other problems associated with ethanol production. Low input, high diversity biofuels are a solution that helps with both prairie restoration and wildlife restoration.
Defined by Dr. David Tillman, a Regents professor at the University of Minnesota, low-input, high-diversity biofuels are high-diversity mixtures of plants grown with low inputs on agriculturally degraded lands. These plants are then mowed, collected, and converted into usable energy. This picture shows plots of LIHD grasses being grown at the University of Minnesota. There are many possibilities for LIHD biofuels. Dr. David Tillman proposes that 13% of global petroleum consumption for transportation and 19% of global electricity consumption can be provided by LIHD biofuels. He also states that 15% of current CO2 emissions can be eliminated.
There are a few problems with traditional biofuels, starting with carbon debt, which is a measure of the amount of carbon that is released when land is converted to cropland over the first 50 years. This can take a very long or very short amount of time to repay and repair for the carbon debt. There is also a chemical impact on the environment from traditional biofuels creation and production, and which can be widespread and have unknown effects very far away and very locally. Just as well, corn and soy biofuels impact the food industry, as you use the crop to turn it into fuel instead of food. Traditional biofuels still need in both production and transportation fossil fuels, so they are not separated from fossil fuels. Lastly, there's a large issue with water usage. It can take between 3 and 12 gallons of water per 1 gallon of ethanol. Using the number in the blue box and 6 gallons per 1 gallon of ethanol average, there is possibly 88,860,000,000 gallons of water used to make ethanol in 2015. This is a graph from Dr. Tillman's paper showing the inputs and outputs between different biofuels, such as corn grain ethanol, soybean biodiesel, biomass electricity, biomass ethanol, and biomass synfuel. As you can see, corn grain ethanol has a very high output, but comparatively to its input, it is very inefficient. Going over to biomass electricity and biomass ethanol and biomass synfuel, you see they have a lower output, but their inputs are very small, showing a greater amount of efficiency overall.
There are many benefits of LIHD biofuels. They provide needed habitat for bird and insect populations because it resembles their natural habitat. It makes the most sense to implement LIHD biofuels near existing prairie reserves, increasing prairie restoration. Due to the high diversity of plant species, LIHD biofuels are resilient to things like fire and disease, and they are carbon negative due to their dense root mass that sequesters mass amounts of carbon. Because we use machinery and not manual labor, it is easy to implement LIHD biofuel plants on the landscape. LIHD biofuels are more beneficial to the soil than corn because perennial grasslands add nutrients to the soil and eliminate soil erosion. LIHD biofuels are more sustainable than traditional biofuels because the output of energy exceeds the input of nutrients as opposed to corn, which requires substantial inputs. And they help combat invasive species by taking up the space with plants native to North America like switchgrass. Here we have an image that shows that as diversity of species increases, so does energy output. On the bottom, there's number of plant species, and as the number of plant species rises, so does biomass energy. And when on degraded lands, LIHD biofuels still produce 51% more energy than corn ethanol while continuing to improve that land.
In 2007, Minnesota's legislation passed a state statute that charged the Board of Water and Soil Resources with acquiring existing easements for the growth and furthering of research in perennial bioenergy. With an interest in alternative biofuels, the University of Minnesota Morris attempted to create a biomass gasification system that would help them go carbon neutral. First, the U of M Morris identified the most local and abundant biofuel sources and focused on finding an energy source that was dense enough to keep a high energy efficiency. Though their project was not successful, projects like this show that there is a real interest in LIHD biofuels, and if a system is created, LIHD biofuels could potentially produce a lot of energy.
Our thought was, what if we took 10% of current Minnesota corn cropland and dedicated it to LIHD biofuel development? The question then becomes, where to site this development? We use GIS to target the most optimal locations for LIHD biofuel development.
This map depicts Minnesota protected lands and native prairie. The lighter green represent GAP 1 and 2 protected areas. Both of these areas are permanently protected from all conversion. However, they differ slightly. GAP 2 protected lands do receive some management, whereas GAP 1 lands are uninterfered with. Due to variation in Minnesota climate, these prairie lands are very resilient landscapes. As a result, we must conserve these areas which promote biodiversity. This map depicts 2014 corn crops in Minnesota. The majority of corn crops are located in southern Minnesota. As shown by the images and previously stated, corn crops have high inputs and high energy sprawl. Our GIS investigation models the effects of converting 10% of Minnesota corn cropland to low-input, high-diversity biofuel development. First, we used raw data of GAP 1 and 2 protected lands from the National Land Cover Database. Then, using the Euclidean distance tool, created a buffer zone around these areas. We then overlaid that intermediate map layer with the corn 2014 layer from the previous slide in raster calculator. To find 10% of current corn crops, we used trial and error when inputting numbers until we arrived at about 3 kilometers representing 10%. This is the final map created from the model, which displays optimal locations for low-input, high-diversity prairie. This map displays our proposed LIHD prairie land in addition to GAP 1 and 2 protected lands and current prairie reserves. Previously, Minnesota had about 18 million acres of native prairie. However, due to numerous factors including population growth, only about 1% or 180,000 acres of native prairie remain today. Converting 10% of corn crops effectively restores some of this lost prairie. In addition to increasing prairie, our low-input, high-diversity land connects many islands of prairie habitat. This is incredibly important for increasing biodiversity and landscape resilience.
So what we found was about 100,000 acres of current Minnesota corn cropland are located within 3 kilometers of current protected prairie land. This amount of acreage is a huge improvement to the current 180,000 acres of current protected prairie land. Under current ethanol production standards, 100,000 acres will yield about 512 gallons of ethanol, which does not put a dent in current production. So the takeaway is 100,000 acres of land is a huge improvement to current biofuels and prairie restoration while taking almost nothing away from current ethanol production.
In conclusion, ethanol, while heavily subsidized, has many negative environmental impacts. LIHD biofuel crops have many benefits, including increasing habitat and biodiversity, restoring degraded lands, and sequestering carbon. Converting 10% of corn to LIHD crops does more good than harm, and using LIHD crops could double current prairie reserves. Although ethanol was the first step to biofuels, we still have a long way to go.